Welcome back to The Explainer. I am absolutely thrilled you're here today, because we're going to explore something that's literally right in front of your eyes, yet completely invisible until it interacts with the world. Today, we're mapping the invisible architecture of everything you see. Our main character for this whole journey, a single glowing particle of energy called the photon. We're going to follow the epic narrative of this tiny traveler from its birth deep in the cosmos all the way to its final miraculous destination right inside your mind.
Okay, let's dive right into this. Just imagine the very first thing you experienced this morning. Before you even fully woke up, light was hitting your eyelids. It feels like such a simple everyday thing, right? But that light, it isn't just an alarm clock. It's actually the universe's oldest, most mysterious form of energy. That morning light is literally a cosmic traveler, finally completing an unimaginable journey just to gently wake you up. Now, to truly appreciate this, we kind of have to understand how unique light is compared to other types of energy. Take sound, for instance. Sound is, well, it's needy. It needs a physical medium, like air, water, or the ground, just to travel. You remove that medium, and sound dies. But light? Light is completely independent. It doesn't need air or water or anything. It propagates freely through the pure vacuum of space. I mean, think about the astronauts on the moon in 1969. They had to use radios because their voices literally couldn't travel in space. And yet, sunlight reached them perfectly undisturbed, blazing across 93 million miles of absolute nothingness. So here's the crucial point. Our photon hero absolutely refuses to wander. When it's moving through a clear, uniform medium, it travels in perfect, absolute, straight lines. In physics, we call this rectilinear propagation. If you've ever stood in a dusty room and seen those sharp shots of sunlight beaming through a window, you've seen this in action. And because light travels so dependably straight, we can harness it. It's the exact principle behind ancient pinhole cameras, and spoiler alert, it's exactly how your own eyes work too. But what happens when our street-traveling photon hits a wall it can't pass through? It bounces. We call this reflection, and it operates on this flawless geometric symmetry. An incoming ray, the incident ray, strikes the surface at a specific spot. Let's call it point O. If we draw an imaginary perpendicular line right there, the normal, we see the golden rule of reflection. The angle of incidence always, exactly, equals the angle of reflection, every single time.
All right, that's when light bounces. But what if our photon can cross a boundary, like passing from the air into a glass of water? Suddenly, the density changes. And because of that, the photon actually changes speed. And when light changes speed, it bends. We call this refraction. It's this wild deception of the eye. It's exactly why a pencil looks broken when you drop it in a glass of water. And this bending isn't just random, it's perfectly predicted by Snell's law, which tells us the ratio of the angle of incidence to the angle of refraction is a constant.
And you know what? This exact phenomenon builds into something you see every single clear night. Have you ever wondered why stars twinkle, but planets just kind of glow steadily? It all comes back to refraction. Stars are incredibly far away, so they act like tiny point sources of light. As that starlight hits Earth's atmosphere, it bends through shifting layers of different temperatures. This constantly shifts the star's apparent position, making it flicker. Planets, though, they're much closer. They act as larger disks of light, so all those little refractive fluctuations just average each other out. No twinkling. So, once humanity figured out that glass could bend light, we learned to harness it using tools called lenses. There are two fundamental shapes here. On one side, the convex lens. It curves outward, it's thicker in the middle, and its superpower is gathering our traveling photons and converging them down to a single focal point. On the other side, the concave lens. It curves inward, thinner at the center, and it does the exact opposite. It scatters or diverges the light rays outward. So one gathers, one scatters. And we don't just guess how much these lenses bend light, right? We measure it with incredible precision. Whether it's Galileo in his 17th century workshop or the eyeglasses sitting on your nose right now, we measure a lens's power in a unit called diopters. The math is beautifully simple. Just take the reciprocal of the focal length in meters. So, a lens focusing light at 25 centimeters, that's 0.25 meters, has a power of 4 diopters. The shorter the distance to the focal point, the more powerfully it bends the light. Now let's look at the anatomy of the light itself. What looks to you like a plain, bright beam of white light is actually hiding a spectacular secret. When white light hits a glass prism, something magical called dispersion happens. Because white light is a mix of many wavelengths, and each wavelength changes speed just a tiny bit differently in the glass, they all bend at slightly different angles. The light literally breaks apart into a brilliant rainbow, violet, indigo, blue, green, yellow, orange, and red. VIBGYO.
But you don't even need a glass prism to see this. Nature performs this massive physics experiment for us after every single rainstorm, using millions of tiny raindrops as individual prisms. And it happens in this beautifully precise three-step sequence. First, sunlight enters the drop and refracts. Then, it hits the back wall of the raindrop and reflects internally. Finally, it refracts a second time as it exits. Because all those wavelengths bend at slightly different angles, millions of raindrops work together to paint this massive, perfect arc of color across the sky. But here's a crazy thought. To recreate that pure white light, you don't actually need the whole rainbow. Incredibly, you only need 3 primary frequencies: red, yellow, and blue. If you mix these at the right intensities, boom, white light. And even cooler, if you pair them with their complementary colors, like matching red with green or blue with orange, they mathematically reconstruct right back into the pure, invisible beam of white light we started with. Okay, now we reach the grand finale of our photon's epic cosmic journey: the human eye. This is a 2.3-centimeter biological marvel that evolved millions of years before the first camera. Just watch how this works. The photon passes the transparent cornea. The muscular iris regulates the pupil to let exactly the right amount of light in. Then our own internal crystalline lens uses tiny muscles to dynamically adjust its shape in real time, focusing that photon directly onto the back wall of the eye, the retina. Once the light hits the retina, it meets this incredible biological sorting system. The retina is packed with 2 distinct types of photoreceptors. We've got about 7 million cone cells, which are sensitive to bright light and give us our sharp central vision and color. Then we have over 120 million rod cells, sensitive to dim light, giving us night vision and peripheral sight. Together, this living architecture translates ancient photons into the 10 million distinct colors and shapes that make up your reality. Of course, biological systems aren't always mathematically perfect, right? Sometimes your eyeball is just slightly the wrong shape. If you have myopia or nearsightedness, your eye focuses the light just a bit too early, right in front of the retina, so distant objects blur. With hypermetropia or farsightedness, it focuses behind the retina. But remember those lenses we talked about earlier? We can put a diverging concave lens in front of a myopic eye or a converging convex lens for a hypermetropic eye, perfectly redirecting that photon so it lands exactly where it needs to. Before we finish up this explainer, let's step outside and look up at the sky one last time. Why does it change color so dramatically throughout the day? Well, it's entirely due to a phenomenon called atmospheric scattering. As light plunges through our atmosphere, it runs into localized moving particles: dust, gas molecules, radiation. These particles basically play a chaotic game of pinball with our photons, forcing the light to deflect and deviate from that perfectly straight path we started with. And this scattering changes based on the time of day. At noon, the sun is directly overhead, so the light has a short path through the atmosphere. The shorter, high-energy blue wavelengths hit those particles and scatter everywhere, flooding the sky with blue. But at sunset, the sun is low. The light has to travel a much longer, thicker path. By the time it reaches you, almost all that blue light has scattered away. Only the tough, resilient, long wavelength red and orange photons survive the trip to hit your eye. And here's the absolute kicker. All of this, every reflection off a lake, every refraction through a raindrop, every signal hitting your optic nerve, it all happens at a speed that literally boggles the mind. 299,792,458 meters per second. That staggering number is the speed of light in a vacuum. It is the absolute, unbreakable speed limit of the universe. And it's the frantic, unyielding pace at which this invisible architecture is constantly constructing reality around you. So, I'm going to leave you with this final question. When you open your eyes tomorrow morning, are you just going to see the world, or will you witness the universe's fastest, oldest energy completing an epic cosmic journey right inside your own mind? I really hope this explainer changes the way you look at a simple beam of sunlight from here on out. Keep questioning what you see, appreciate the invisible architecture all around you, and I'll catch you next time.